Welcome to Math with Malia. Today we're doing Savvas enVision Algebra 1, Topic 3, Lesson 5, Scatter Plots and Lines of Fit. After this lesson, you'll be able to use a scatter plot to describe the relationship between two data sets. We have some new vocabulary to learn: negative association, no association, positive association, and a trend line. Since we're in the topic about linear functions and linear equations, we're going to talk about linear lines of best fit and scatter plots. For the model and discuss, we have this data. Nicholas plotted data points to represent the relationship between screen size of a television set and the cost of that TV. Everything about the televisions is the same except for the screen size. And so we can see as the screen size increases, the cost is going to increase as well. And if we were to make a guess, like rough estimate of those data points, we can see that it does fit approximately a linear relationship. We can see that we can make a line, a straight line through those data points that covers most of the data points. I have 1 point above and 1 point below. Again, in the real world, we do not typically see perfectly linear situations or data, but we can represent what best fits the data. And does it make sense that the bigger the screen size, the more the TV will cost? Well, yes, that makes sense. Part C, where do we think the point for a 46-inch television would be? So we didn't have a 46 screen in our table, but we can make an estimate based on this data. So 46 is going to be right here. So if we were to draw approximately where it would be, we could say it would cost approximately $450. So about $450 for the 46-inch television, which makes sense. It's right there in between $400 and $480. And how about a 60-inch television? Okay, so 60 inches is going to be after the 50-inch. We could look at the increase from 40 to 50 inches, and it increased by $200. So maybe going up another 10 inches, it would go up by another $200. So we could estimate maybe a 60-inch television would cost about $700 based on this data if it were to follow the same trend. Example 1, understanding association. So here we have another graph, and we're measuring temperature after sunrise. Our input, or our x-axis, measures the hours. Again, our units of time are generally going to be on the x-axis. And our y-axis, or our output, is measuring the temperature outside. And we can see all of these data points. It's not perfectly a straight line, but we can see that in general, as the time after sunrise increases, as we move to the right, then we also move up. Our y-axis, our temperature also increases. So we can see that if both input and output increase, then this is called a positive association. You can see that if I were to make a line to best represent the data, it has a positive slope. So this is called a positive association when as x increases, y also increases. In this data set, the temperature after sunset, you can see that as the time increases, the temperature is decreasing. So they're going in opposite directions. As x is increasing, as my inputs increase, then my outputs will decrease. This is called a negative association. Again, if we look at that slope of that line, it is a negative slope. So negative slope gives us a negative association. Association really talks about the relationship between the two values. Does one value affect the other value? So yes, the time after sunset does affect the temperature. Even though it's in an inverse relationship going in opposite directions, the time in hours after sunset does have an effect on the temperature. So there is an association, or there is a relationship between those two values. Part C. Now we're measuring rainfall after sunset. So the time in hours after sunset and the amount of rainfall, you can see we have points going up, we have them coming down. Can I really draw a straight line through this? Well, no, because it kind of goes up and then it goes down, it comes up again. We don't really see a clear pattern, a clear relationship, so there is no association. The time after sunset does not affect the amount of rainfall. We can have rain in the morning. We could have rain right at sunset. So the time after sunset does not have a relationship or does not have an association with the amount of rainfall. Try it number 1, describe the type of association. So it's either positive, negative association, or no association. So again, let's look. What's the general trend? If I'm going to estimate a line through the data, I can see that it has a positive slope. So part A is a positive association, and it's linear, okay, because we can make a straight line. We are again in the topic for linear functions, so our associations are going to be linear. For part B, can I draw a nice straight line? Well, I could draw a line here. That doesn't really fit the data. I could do a line there. That doesn't really fit the data. I could do a line there. So we can't draw a clear linear graph to represent the data, so there is no association for part B. There's no relationship between whatever those values represent. Example 2. Trend lines, and what does a trend line model in a scatter plot? So after we have our data graphed in our scatter plot, then we can draw what's called a trend line, also called a best fit line or line of best fit. Okay, it's just the line that best fits all of the data. It doesn't have to go through every single data point, but it's going to do the best fit. Okay, so a trend line, again, approximates the balance of points. So we want the same number of points above the trend line as we have below the trend line. So here we have our graph, our scatter plot representing electric cars sold. Our input is measuring the years starting in 2010, so how many years since 2010, and then the number of cars in thousands sold is our output. You can see we have that positive association. As the years increase, we sell more electric cars, okay? And we can see that we have 2 points that are exactly on the trend line. We're going to use those 2 points in a minute. Let's count how many we have above the trend line. There's 1, 2, 3, 4. This one's kind of far above. You can see some of them are closer to the trend line, some are farther away, but we have 5 points above, and we have 4 points below. So it's approximately balanced. It doesn't have to be exact, but we don't have all of the data points on top and only 1 or 2 on the bottom. Okay, so we have balanced the data. We've split the data with our trend line. So after we have that, using that trend line, we can come up and write the equation for that line. We know how to write an equation for a line. We can use our slope-intercept form, y equals mx plus b, or we can also use point-slope form. We just have to identify the slope. Okay, so we have to first figure out the slope of that trend line. We're going to do that by using these 2 points. Okay, so we're going to find the change in y. Remember, our slope is the change in y over the change of x. So let's find the change in y. I go from 328, and my first point is 118. So there's my change in y over my change in x. It's 8 minus 3. Okay, and we'll see the math done on the next page. After we've done our calculation, we get approximately a slope of 41.8. Okay, using the 2 points that are on the trend line, when you calculate slope, you want to use 2 points that are exactly on the trend line. And then we can plug that slope into point slope form. So either using the first point or the second point, it doesn't matter. They're using the first point. So here's our y value of the first point. Here is the x value of the first point. And then, of course, we plug in our slope there for point slope form. So we used point slope form here. And then to turn that into slope-intercept form, well, then we need to distribute the 41.8. So we distribute then 41.8 times negative 3 is negative 6.4. Sorry, it's not. And then we add 0.119 and we get negative 6.4. So we just solved the point slope form. We solved for y and turned it into y equals mx plus b. So our trend line that models the data is here. We can see our y-intercept would be at negative 6.4, and our slope, the slope of that trend line, would be 41.8. We use this trend line to make predictions. Okay, this can help us to make predictions. As we did in the critique at the beginning of the lesson, we could guess how much a 60-inch TV would cost by using the trend line. Okay, so use our equation for the trend line to make predictions. When we don't have a specific data point value, then we can use that equation to calculate an estimated value. Part A, what trend line and slope-intercept form models the data in the first graph of the triad of the previous example? So we're going to go back to triad number 1, part A, and looking at this trend line, we're going to try to write the equation. So let's see how well I did drawing this. I have 1, 2, 3, 4, 5, 6 points above, 1, 2, 3 below. I'm going to try to make this a little bit more balanced. So let's redraw our trend line. That might be okay. That might be okay if I count this one below. So that's 4 below and 1, 2, 3, 4, 5 above. Okay, pretty good. So let's use this first point on the trend line, and let's say this one's on the trend line. So let's use those values to find the slope. So this point is at 8,7, and this point is at 1,1. So we're going to find our change in y over change in x. Our slope is going to be 6/7. And then pick either point and put it in point slope form. So y minus 1 equals 6/7 times x minus 1. Do our calculations. Plus 1. And so we have our equation. Y equals 6/7 x plus 1/7. That is our equation in slope-intercept form that represents that best fit line. Part B, explain why there could be no data points on a trend line, yet the line would still model the data. Well, again, the trend line just has to be a best fit. It just has to have a balance, the same number approximately above the trend line as below. So even if no points are exactly on the trend line, as long as there is about an equal number above the trend line as below, then we can still estimate the general pattern. Example 3, interpreting trend lines. This table shows the amount of time required to download a 170 gigabyte file for various internet speeds. Assuming the trend continues, how long would it take to download the file if the internet speed is 800? So look in our table, do we have 800? We do not have that data recorded, so we're going to need to approximate that. Okay, we're actually extrapolating the data. We have data beyond our table set, so we have to use a trend line to be able to approximate the value. Remember, our input is the speed and the time to download is our output. Okay, so we made a scatter plot. We just graphed these points, 100, 28.62, 200, 14.3, 300, 9.5. So these are our ordered pairs, and we just plotted those. We can see our scatter plot. We drew our trend line, so we have the same amount above as below. So we have 1, 2, 3 above and 1, 2, 3 below. We're going to choose these 2 points that are exactly on the trend line to calculate our slope. So those are our 2 points, again, exactly on the trend line. Use 2 points exactly on the trend line to calculate the slope. So our slope, again, is change in y, 5 minus 10, over change in x, 580 minus 320. And we do our calculations, we should get approximately 0.02. Plug that into one of the points. So let's just use the first point in 2-point slope form. So y minus the y value equals the slope times x minus the x value is 320. And we do our calculations. We get y equals negative 0.02 x plus 16.4. So again, we'll distribute the negative 0.2, 0.02, and then add 10. Then, using our equation, our linear equation for the best fit line, we can plug in our new input. So we're just going to plug in 800 for our x value and solve for y. And if we do those calculations, y is going to equal 0.4. So it would take 0.4 minutes to download 170 gigabytes. What is the x-intercept of the trend line? Is that possible in a real situation? So remember, our graph, our y-axis was measuring download speed, okay? Download speed. And our x-axis was measuring internet speed. So if it's the x-intercept, that means y equals 0. So then our download speed would be 0. Is it possible to download 170 gigabytes in 0 seconds? Well, no. Or minutes. It's not going to be instantaneous. So it's not possible in this real world situation to have instantaneous download speed. Maybe one day in the future. So that's our concept summary for scatter plots and trend lines. Remember, positive association is when both are going up. So x is going up and y is increasing, is going up as well. Negative association is when x increases and then y is decreasing. We have a negative slope. Okay, so our trend line would be positive for a positive association, and our negative association will have a negative slope. And representing our graphs, that trend line will cut the data points in half with approximately the same amount of data points above the trend line as below. And we can use 2 points exactly on the trend line to calculate the slope and use point slope form. So remember, you're first going to use point slope form and then turn that into slope intercept form. And then do your distributing, and you'll have y equals mx plus b to represent your trend line. If you have any questions, put them in the comments, and make sure to come back for lesson 6.